Welcome, everyone. Today, we're very happy to have Sandipan Kundu from Johns Hopkins University, and he's going to be telling us about swampland conditions from CFT. Okay, please take it away, Sandipan.
Thanks, Nima. Thank you very much for the invitation. So this talk is based on a recent paper of mine. Sorry, something happened. Yeah. So the main idea of this talk is actually very simple. The goal is to find the space of EFTs that can be UV completed from general principles and symmetries. This is not at all a new idea. This idea has been around for a long time, but in recent years, it has gained a lot of attention. For example, Conformal Bootstrap program is an example of this general idea. However, as I said, this is not a new idea, and there are many examples of this general idea in physics, in high energy physics. So one of my favorite example is this result from Adams, Arkani, Hamed, Dubosky, Nicolis, and Ratazze. This is a remarkable result. So the first step is to start with a scalar field with a shift symmetry. So here is the, for some reason, okay, let me give a second. For some reason, my pencil does not work. You cannot see anything on the screen.
No, we can't. Are you writing on the screen?
Yeah, let's see. Okay, now it works. So the first step is to write down a kinetic term, which is a standard kinetic term. Then there can be other interaction term. The term that I'm going to focus on is basically a higher derivative interaction term, something like this, with some coupling constant mu. So this interaction is non-renormalizable. So this is basically an effective field theory which is valid up to some cutoff scale. What these authors showed is basically just from some general condition on the scattering amplitude, they showed that this effective field theory can be UV completed only if mu is positive. So in other words, if mu is negative, there is no way this effective field theory can be UV completed. So to me, this is actually a really important result because it represents a significant departure from our traditional understanding of effective field theory. For example, it's not that everything goes. So there are effective field theories that can never be UV completed. More practically, this result actually played an important role in the proof of the 4D theorem. So this has applications as well. This bound is actually part of a more general idea. So it's the idea of Swampland by Fafa. So it is expected that there are Swampland of effective field theories that can never be UV completed. So in other words, only a subset of all effective field theories come from some UV complete theory. And actually, there are two completely different approaches one can take to actually understand this idea. First of all, one can start from some UV complete theory and look at what kind of effective field theories one can generate from that UV complete theory. But any such construction will depend on the exact UV complete theory that you start with. There is a second approach which is completely within the framework of effective field theory. It's basically just from some consistency condition of quantum field theory, you try to figure out whether some effective field theory can come from some UV complete theory, or actually what you do is the opposite of that. You try to rule out effective field theories that can never be UV completed. And generally, whenever you have dynamical gravity within your effective field theory, then this UV complete theory is obviously a theory of quantum gravity. The bound of Adams et al. Actually, it's not an accident. There are many such bound that one can derive in effective field theory. In fact, there is a growing body of literature with similar precise bounds on IR couplings from UV consistency. Just to give you an idea, this is a list of many such results. If I'm missing some references, I apologize. The point is that there are many such bounds one can derive just from some general condition about scattering amplitudes. All these arguments, they have a couple of things in common. So all these arguments, they actually don't depend on the details of the UV complete theory. But these bounds are derived under the assumption that the scattering amplitudes obey certain conditions. For example, for 2 to 2 scattering amplitude, it is generally assumed all these bounds, they at least assume these 4 conditions about the 2 to 2 scattering amplitude. The amplitude is analytic in the upper half complex S plane. Also, it's assumed unitarity. So when I say unitarity, I just basically mean that the partial of expansion has the right positivity condition. Also, the amplitude is crossing symmetric, and there is a requirement about how fast the Regge amplitude can grow. So this condition actually is very important for the derivation of any such bound. It is assumed that the large S limit of the forward amplitude cannot grow faster than S square. So this is a key assumption that's required to derive any such bound. But there is something conceptually unsatisfying in the sense that these assumptions, even though these assumptions are well motivated, they have not yet been rigorously established. So that's one thing that's kind of unsatisfying. For example,
question,
yeah,
about this. So most of these things were focused on situations where you have a free theory plus irrelevant interactions. Do you think similar strong constraints would hold for if you started with an interacting CFT plus irrelevant deformations?
You mean these conditions, right?
Sorry?
You're talking about these conditions. Which conditions?
Right. And yeah.
So in general, actually, I'll talk about, so the condition that's kind of tricky is probably the Regge boundedness condition, which is, as you said, it's not very general. In situations where there is a mass gap, probably you can argue that this is true, but in general, I don't think that I don't think there is a general argument which says this has to be true. So, but the other conditions, they are more or less better understood. That's what I would say.
Right, but I was asking, so the literature that you mentioned shows that there's a lot of constraints if you start with a free theory without irrelevant interactions, starting with that Adams et al. Paper. Do you expect there to be as strong conditions if you start with an interacting CFT and add irrelevant interactions?
I don't see why not, but actually, I'll give you the construction that I'm going to talk about. Probably that will answer your question anyway.
Okay.
So they are basically, we will talk about some strongly coupled generalized free CFT, and there will be deformation. We can actually constrain those with deformation.
Okay, great. Yeah, thanks.
Okay. So as I said, the Regge boundedness condition, actually, one can justify this condition when there is a mass gap in the theory, where actually this Regge boundedness condition is actually implied by the Froissart bound. But as I said before, Froissart bound is not applicable when massless states are present. So the validity of the Regge boundedness condition in general is not very clear. And actually, this is kind of annoying in the sense that some of the effective field theories that one would like to constrain are effective field theories of massless number-Wilson bosons. So that's kind of it's in that case it's not completely clear if the Regge boundedness condition is applicable. There is another technical problem that is associated with all these arguments. So it is technically challenging to actually incorporate dynamical gravity because of the graviton pole. So generally, most of this argument they talk about the forward limit. So even if you take the tree-level graviton exchange diagram and take the forward limit of that particular diagram, you get a pole at t equals to 0. So because of this pole, actually all these arguments are a lot more subtle when you have graviton. But very recently, this problem has been addressed by Kernhuart, Mazak, Rastelli, and Simons-Duffin. So what they did is the following: they studied the scattering amplitude not in the forward limit, but at finite impact parameter, which solves this issue with the T-channel pole. So, and their argument actually works in any spacetime dimension above 4. But if you look at this tree-level graviton exchange exchange diagram, validity of the Regge boundedness condition is even more unclear, because even the tree-level scattering amplitude, it grows as S squared. So the restriction that for large S, the amplitude does not grow fast. The amplitude grows slower than S squared is a strong, really, it looks like a strong condition. So the main point that I'm going to emphasize in today's talk is that all these loopholes can be avoided by studying effective field theories in ADS. So that's the main point that I'm going to emphasize. So the idea is actually, roughly speaking, the idea is basically studying effective field theory in a box, where this box is ADS. The reason why this is advantageous is because there is a dual CFT description in one less dimension from Conformal Bootstrap. So this duality is well understood from Conformal Bootstrap. So because of this duality, we can find the space of effective field theories in ADS that cannot be UV completed directly from Conformal Bootstrap axioms. The reason why this is nice because because Conformal Bootstrap axioms, they are well established and well understood. So there is no ambiguity in this axioms. Another advantage of this framework is basically inclusion of gravity is trivial, as I'll explain in the second half of the talk. Any question? Okay, so this is exactly what I'm going to show. I'll show that scalar effective field theories with higher derivative interaction, all these coupling constants of higher derivative interaction, they must obey certain positivity, monotonicity, and lock convexity conditions. Otherwise, these effective field theories will be in the swampland. So that's the main claim of this talk. And then if somebody wants, they can take the large radius limit and they can recover flat space bounds. However, I should mention that there are cases where in the flat space limit, you don't actually get a precise bound. And later, I'll give you an example. Another thing that one would like to address is the following. So all these conditions that I discussed in the beginning about the 2-to-2 scattering amplitude, it is of interest to actually explore whether these assumptions are valid or not. And actually, I'll make some precise comment about the validity of these assumptions from Conformal Bootstrap. So this is the outline of the rest of the talk. Let me pause for questions. Okay. So let me now make everything more precise. So this is the theory that I'm going to discuss today. This is a effective field, scalar effective field theory in ADS, where I have a single scalar field. So then there is the mass term. So this scalar field can be massless or massive, but I'm going to assume that mass square it's not negative. And then there are all these higher derivative interaction terms. So I'm not going to assume anything about the coupling constants lambda to begin with. So the goal is to actually impose constraint on this lambda coupling constants. Let me make some comments about this setup. I start with the setup with no dynamical gravity. So that's just for simplicity. So as I said before, inclusion of gravity is trivial. So I'll include gravity in the second half of the talk, just as a generalization of this setup. Also, this effective field theory will be analyzed at tree level. So which will be implemented by taking this overall coupling constant mu. We take that to be positive but small. So if all the quantities will be computed at the leading order in mu. The third condition that I'll impose is the following. The radius of ADS is large compared to the cutoff scale associated with this effective field theory, which is this condition. And as you can see, there are dots written here. So that means basically there can be other things that one can include, but all the bounds that I'm going to talk about, they will not depend on these dots. But I'll make one assumption about what other things can there be in this system. So I'm going to assume that no light particle with spin greater than 2 is present. So there can be high spin particles, but their mass is above the cutoff scale. So I'm going to assume that. And also, if you look at the effective field theory, there is no phi cube interaction. That does not mean a phi cube interaction cannot be present. What I mean is basically, even if there is a phi cube interaction, that will not affect the final bounds. However, there is one important thing that I should say. If there is a phi cube interaction in low spacetime dimension, it can actually make the flat space limit more subtle. And finally, I'm going to I should make some comments about other higher derivative interactions. So if you look at interaction terms with, let's say, 12 or more number of derivatives, actually one can show that there are other higher derivative interactions that one can write down, which are completely different from this kind of interaction. So I'm not assuming that these other higher derivative interactions are not present. But the statement is the following. If these other higher derivative interactions are present, they will not affect the bounds that I'm going to obtain today.
So you're going to find bounds on lambda k, but not on the lambdas for these other higher derivative terms?
Exactly. The reason is basically all the higher derivative terms that cannot be written in this particular form, they will actually produce subleading contributions. So that's why they are not important. So all the leading contribution to any amplitude or in my case, like the things that I'm going to compute is basically some CFT correlators. These are the only interactions that will produce the dominant effect. Any other question?
So you don't have any restrictions on the lambdas?
To begin with, no.
Begin with, no.
So
And
go ahead.
And is there any natural scale in the system?
Okay, yeah, that's a very important question. So if generally the way you get this kind of effective action is basically start from some UV theory, you integrate out above some energy scale, and that scale will appear everywhere in this effective field theory. But the goal is basically, for me, the goal is actually, I'm not going to assume that it's coming from some UV complete theory to begin with. So I'm just, so far, I'm just writing down this effective field theory. So all these things should actually follow from the analysis. So the expectation is the higher derivative, all the higher derivative interactions, they should be suppressed by the cutoff, by some cutoff scale with the overall coefficient order 1. So my goal is to basically actually at least derive some version of that from my analysis. Any other question? Okay. So this is the setup. Then thanks to Hemsker, Penedones, Polchinski, and Sully, we know that there is a dual CFT description in one less space-time dimension. This actually follows from a very nice observation that they made. There is a one-to-one correspondence between scalar effective field theories in ADS-D and perturbative solutions of crossing symmetry in CFT D-1. So this is basically a scalar version of ADS CFT from Conformal Bootstrap, at least at the level of 4-point correlators. So this from Conformal Bootstrap, this is actually very well, this scenario is very well understood. So in this duality, just like ADS CFT, the scalar field in ADS is dual to a scalar primary O. And the dimension of this scalar primary is given by the standard dictionary. But notice that there is no dynamical gravity so far. So which is implemented by taking this central charge to infinity. So the central charge is defined as, if you consider 2-point function of the stress tensor, so it has some overall coefficient times the standard tensor structure. So this CT is the central charge that I'm talking about. So I'm going to take the central charge to be infinity. What that means is basically, that means the stress tensor actually decouples from the low energy spectrum. And I take central charge to be infinity, but I keep the gap scale fixed. Where the gap scale is basically some cutoff scale in the effective field theory times RADS. So in the order of limit, I take CT to be infinity first, then I take lambda gap to be large but fixed. So that's how you get a dual theory where there is no dynamical gravity. We can actually say a lot more. So to do that, first let's take all the interactions to be exactly 0. So we have a free theory in ADS. In that case, in the CFT side, all the in-point correlators must factorize into 2-point correlators. So that's why the dual is said to be a generalized free CFT. But still, it's a strongly coupled system because we are taking the limit where central charge is large. So this is a strongly coupled system with large number of degrees of freedom, which has correlators like a free CFT. And also, there is something really interesting. Even though we started with a single primary scalar operator, just from the crossing relation, one can show that there has to be other composite primary operators, which are written here, like they have this particular form. So they are the double trace operators, which are denoted by this particular notation with subscript n and l, where l is the spin and n gives you the dimension of these composite operators. For n is actually an integer, n is a non-negative integer, and l is also an integer, but l is even. Because odd spin double trace operators, they don't exist when they are when you consider double trace operator of the same operator, odd spin operators, they don't odd spin double trace operators, they don't exist. So from crossing, one can show that this double trace operator must exist for all non-negative n and all even L greater than 0. So even if you start with a single primary operator, this double trace operators must be there to make the CFT consistent. Now we can add interactions. So what it does is something really interesting. So the dual CFT remains almost the same. Only thing that changes is basically the OP coefficients receive some correction, and also these double trace operators, their dimensions receive some anomalous contribution. And there is a very nice relation between this anomalous dimension and the bulk interaction. So for example, if you add some 5⁴ interaction in ADS, that gives anomalous dimension to double trace operators with spin 0. Similarly, if you add an interaction like this for phi² box square phi², this leads to anomalous dimension for double trace operators with spin 2. Similarly, if you have phi² box to the power 4 phi², you get anomalous dimension for spin 4 double trace operators, so on and so forth. So there is a very nice relation between this set of anomalous dimensions and bulk and ADS interactions. Any question? Okay. So we started with this general effective field theory, which gives anomalous dimension to all double trace operators, and the anomalous dimension is actually proportional to lambda k. So anomalous dimension for spin k is proportional to lambda k for even k. So this is the dual. This is the anomalous dimension in the dual CFT theory. So now I'm going to ask the following question. So I want to know when this effective field theory can come from a UV complete theory. So that's the question that I want to address. But now actually I can ask the dual question, which is easier to answer. The question that I'm going to answer is the following. When this scalar effective field theory in ADS cannot be embedded into a UV theory that is dual to a CFT obeying the well-established CFT bootstrap axioms. So this is the question I'm going to ask. I'm going to analyze this dual CFT and require this CFT to be UV complete CFT that obeys all the bootstrap axioms. Is that clear? Any question?
Is there mixing, or is it direct? Like box to the k always only affect gamma and k, or is there?
So at tree level there is no mixing. So if you consider loops, then there will be mixing.
Yes. Okay.
But the mixing is also kind of well understood. Like if I give you some particular interaction and you consider one loop, what kind of double trace operators will receive anomalous dimension? I think that's kind of known.
Okay.
Okay, so the way I'm going to answer this question is by considering a very specific CFT theorem. It's a theorem about CFT Regge Correlator. So let's consider this specific CFT correlator, 4-point correlator, where these O operators are inserted as shown in the figure. So x plus and this x plus and x minus, they are the standard null coordinates. So this is a Lorentzian correlator. And as you can see, some of the operators are time-like separated. So operator ordering inside this correlator is actually very important, and actually operators are ordered as written inside the correlator. Then I'm going to take the Regge limit, which is before that. Let me note that this is the left Rindler wedge. This is the right Rindler wedge. So the operators are inserted in a symmetric way. So operators in the right Rindler wedge, they are Rindler reflection of the operators in the left Rindler wedge. So for this kind of setup, I can take the Regge limit in the following way. So as you can see, the distance of this operator from the x plus axis is basically, I write that as 1 over sigma. And this distance between the operator and the x minus axis, let me write that as eta times sigma. So the correlator is a function of both eta and sigma. The Regge limit is taken as sigma goes to 0. So I'm going to discuss a very specific theorem for this Regge correlator. So our Regge correlator is a very complicated correlator, and it can have many different forms, but I'm going to assume the following. I'm going to assume that the Regge correlator has this very specific structure. So where there is 1, which comes from the identity exchange, and then everything is imaginary, where the coefficient is basically a function of eta, and in the denominator you have some odd powers of sigma. So you have terms like 1 over sigma, 1 over sigma cube, 1 over sigma to the 5th, things like that. And I assume that this is valid up to some cutoff scale sigma star. So sigma star can be 0, that doesn't matter. Then basically this is valid everywhere, but I'm going to assume that it's valid up to somewhere. One reason why I'm assuming this particular form of the Regge correlator is actually, I think, kind of obvious. It's basically because the CFT dual to the scalar effective field theory that I started with, it will have exactly this particular form. So that's why I'm focusing on this very specific form of the Regge correlator. But in general, for a generic CFT, this might not be it can have, the Regge correlator can have a different form. So the statement that I'm going to make next, it depends on this very specific form of the Regge correlator. Also, like, one may ask the following question, like, why I'm only including even L terms? Why not L equals to 3, L equals to 5, L equals to 1? Why they're not there? One, I can start with all these all these other terms as well, but actually it's very easy to show that the coefficients of all these terms must be exactly 0. The reason is actually very simple. So the reason is actually related to the fact that only even spin operators can appear in the OPE of identical operators. So that dictates that this sum can only have even L contributions. Okay, so now from unitarity, crossing, and analyticity, I can write down a rigorous sum rule for this CL coefficient. So the things that I'm assuming is basically, let me first talk about crossing and analyticity. So these two conditions, they follow directly from the fact that we have an operator product expansion. So crossing and analyticity follow directly from the OPE. And unitarity is basically the statement that OPE coefficients are real, or OPE coefficient of real operator are real. So these are the standard axioms of conformal bootstrap, and by using that, I can derive this sum rule. Not just that, from this set of assumptions, I can also show that this quantity inside the parenthesis, it's positive. So I have a sum rule in safety from which I can actually derive very general condition on this CL coefficient. So this particular Regge correlator can come from a well-behaved CFT only if all the CL coefficients, they are positive for even L. I only have even L here, so all of them for L greater than or equals to 2 must be positive. Not just that, the CL coefficient must decrease monotonically as I increase L, as shown here. So the right hand side, this quantity is actually much less than 1. And finally, there is a lock convexity condition that all the CL coefficients must satisfy. All of them follow from the sum rule. So in any CFT, if I get this particular Regge behavior, then all the CL coefficients must satisfy all of these conditions. Any question?
And you're saying that this form can be derived for generalized free field CFT?
Not for just for generalized free CFT. This form can, so this can be derived when I have a ADS theory which had that particular form. Like if you write down any scalar or even spinning effective field theory in ADS and look at its dual CFT, in the Regge limit, this is the form that you'll always get. And this is one, okay, I should also mention that this theorem that I just mentioned, it does not actually require the operators to be scalar operators. This is a very general theorem. It is true even when the operators have spin. So that means basically in any kind of effective field theory, where you have spinning field or scalar field, this kind of theorem is going to be useful there. So the next step is actually kind of simple and it's kind of obvious. Now I'm going to compute this Regge Correlator starting from the scalar effective field theory that I discussed in the beginning. At tree level, there are only two types of diagrams that I can, two types of Witten diagrams that I can have. This is the exchange diagram if I have a phi cube interaction. If there is no phi cube interaction, this diagram is not there. And then there are contact diagrams for terms like this. So for each such interaction, there is an associated contact diagram. And as I said, if you compute the Regge contribution of all of this, if you have the desired form up to terms that decay in the Regge limit. So the leading growing pace in the Regge limit, as I said before, is the sigma goes to 0 limit. So the leading pace is this one, and then this imaginary pace, which has the desired form, and there can be corrections, but they are always small in the Regge limit. Now the goal is to relate this lambda coupling constants and this CL coefficients. And the relation is actually as shown here. So lambda, let's say lambda 2 gives C2, lambda 4 produces C4, so on and so forth. So basically the relationship is linear. So CL for even L is proportional to lambda L. In this relationship, kappa is some numerical factor that's known exactly. This f function is basically a function of eta, which can be found exactly. This is actually some integral of the harmonic function in hyperbolic space, but it can be computed exactly. So, but their exact form is not important for us. So the important part is CL is proportional to lambda L for even L. Now you can ask me about odd L. What happens for odd L? Actually, the odd L contributions are always subletting. So this relationship is not actually exact. So I have an additional term, which is basically lambda L plus 1, which is the odd term, but this is suppressed by some higher power of RADS. So that's why this can be ignored. So that means basically the odd L interactions are always subletting. So at least from this particular formalism, I'm not going to derive, I'll not be able to derive any restriction on the odd L lambda coefficients. But obviously, as you can see from this relationship, I'll be able to derive strong constraints on even L lambda coefficients. In fact, this proportionality relationship immediately implies that positivity, monotonicity, and lock convexity conditions of CL coefficients imply positivity, monotonicity, and lock convexity conditions for even lambda L interactions. But as I said, there is no bound for odd L. More specifically, let me show you the exact bounds. So this is for the massive case. So this is where this is where m square is non-zero. And I'm going to take mu to be positive as well. And this can be done without any loss of generality. I can just define mu to be positive. And as I said before, I did not assume anything about this lambda coefficient. But it is expected that just from examples, it is expected that higher derivative interactions are suppressed by some cutoff scale where the coefficient is order 1. And one of the goal is to actually derive that statement. First, for if any even k greater than 0, so for k equals to 2, 4, 6, all these lambda coefficients, they must be positive. So that's one condition that this effective field theory must satisfy. The second condition is that as you increase k, the lambda coefficient must decrease monotonically. So in the right hand side, you first get something like sigma star squared times r radius to the power 4. But where sigma star goes to 0 first, then you take r radius to be large. So so this is basically that means basically this is this quantity is suppressed parametrically, the right hand side. And I'm going to actually define this to be 1 over m to the power 4, where m is some cutoff scale in Kundu filter. This is the definition of the scale m. So far that before this step, that scale m never appeared in the analysis. So I'm going to define this to be some cutoff scale. So as you can see now, that means lambda 4 over lambda 2, that must be smaller than 1 over m to the power 4. Similarly, lambda 6 over lambda 4 must be smaller than 1 over m to the power 4. So that means basically this is actually a proof of the statement that as you add more and more derivatives, they are suppressed by higher power of the cutoff scale m with order 1 coefficients. But unfortunately, a similar statement, at least from this analysis, a similar statement does not exist for odd k. Oh, one more thing I should mention. Obviously, since this m is defined here, so one may wish to define the cutoff scale for this effective field theory in a different way. So they can choose some other criteria to define the cutoff scale. Obviously, in that case, in terms of that other cutoff scale, you'll get a different bound. So this particular bound depends on how exactly you define the cutoff scale. Then how do I interpret this bound? The way this bound should be interpreted is that all these lambda coefficient, they must satisfy this monotonicity condition up to a rescaling of the cutoff scale. So for any other cutoff scale m prime, which is basically some order 1 number times this cutoff scale, so there is some rescaling which will make the effective field theory consistent with this monotonicity condition. So that's how this condition should be understood. But let me also make the comment that this positivity condition, it does not depend on the definition of the cutoff scale at all. Then there is the third condition of lock convexity. All lambda coefficients for any k1, k2, and k3, any even k1, k2, and k3 must satisfy this lock convexity condition. Again, this does not depend on how you define your cutoff scale. So this is independent of the cutoff scale. So all these lambda coefficient must satisfy these 3 conditions. Before I proceed, any question or any confusion? Okay. And this is a pictorial representation of the same set of bounds. They must decrease monotonically. They should have this kind of lock convex feature. And the important point is this is essentially a high energy argument. So all these bounds must persist even in the flat space limit, because this is essentially a high energy argument. So one can actually try to compare these bounds with bounds that one can obtain from the flat space scattering amplitude. So that actually can be done very easily, just from the general assumptions about the scattering amplitude. One can write down a dispersion relation for the lambda coefficients. This follows from the work of Adams et al. And from this dispersion relation, one can actually derive the same set of bounds. The advantage is now we can actually have a really physical interpretation of the cutoff scale that I defined in the previous slide. So this cutoff scale is basically the lower limit of integration in the dispersion relation. So that means this cutoff scale M is, at least in this in the massive case, the cutoff scale M is basically the mass of the lightest heavy state exchange in this relative scattering amplitude. Or in other words, it's the energy scale where the imaginary part of the forward limit of the amplitude becomes non-zero. So this gives the cutoff scale a very physical interpretation. So that means basically for massive external states, bounds from conformal bootstrap actually agrees with bounds from the flat space asymmetric space argument. So this should be regarded as a strong evidence in favor of this set of assumptions about the 2-to-2 scattering amplitude. However, I must say that in this CFT analysis, there is a discrete difference between massive and massless fields. And this exact relationship, this agreement between the flat space argument and the CFT argument, this agreement does not work when the external states are massless. So when the scalar field is a massless scalar field. In fact, in general, one can derive this general bounds from CFT. So which is valid even both for the massive case and for the massless case. So the positivity condition is exactly the same. We have similar monotonicity and lock convexity conditions, which are obtained by taking the old relationship and just rescaling lambda k by this result, this quantity, where this overall coefficient n of delta, which is written here, it's a known prefactor, the exact form of which is not important. The fact is that we exactly know what the prefactor is. We just have to replace lambda k by this quantity in the monotonicity and lock convexity conditions. So that will give you the exact bound which is valid for both massive and the massless case. And the reason why in the massive case there is an agreement between the flat space argument and the CFT argument is basically when M is non-zero, M times R radius is very, very large. And that means in this delta is very, very large, which is basically 1. So this prefactor is different from 1 only when we have massless fields. Now, let me include dynamical gravity, which is actually very easy to do. In the CFT side, what it means is basically the central charge is no longer infinitely large. It is large, but finite. So that's the only difference between this and the previous case. So what it means is basically the effect of the stress tensor can no longer be ignored. So when I compute this Regge correlator, now I must include this extra diagram, which comes from a single graviton exchange. And then again, I can find out all the CL coefficients. Now that this is the old coefficients that I had without dynamical gravity, and there is a correction piece. And if you look closely, the gravity part only contributes to L equals to 2. So for L greater than 2, there is no correction. So this immediately implies the positivity, monotonicity, and log convexity conditions remain unaffected for k greater than or equals to 4. So there is only a change whenever you have lambda 2. So lambda 2 is basically, so now what happens is basically when G Newton is non-zero, lambda 2 basically gets shifted by some additional term, which is proportional to G Newton. So you can think of this shift as the gravitational time delay. So to summarize, whenever you include gravity, things like lambda 4, lambda 6, lambda 8, all the bounds remain the same for all these coupling constants. But whenever you have lambda 2, there is a shift, and because of which bounds involving lambda 2 is now different. For example, the positivity, so without dynamical gravity, we had the bound lambda 2 has to be positive. So because of this shift, now lambda 2 can be negative. So it can be, so the strict positivity condition of lambda 2 is no longer there when G Newton is finite. This can look little problematic because if you take R radius to be infinitely large, it looks like the right hand side can blow up, but that's actually not true. So this right hand side can actually be written in a different way, where you have lambda gap in the numerator, but central charge in the denominator. So the large R radius limit is always taken in this particular way to make sure that CT is larger than delta gap, which is larger than 1. So that means the right hand side is always small, even when you take the large R radius limit. But you must see another problem. So this R radius in the numerator means there is no precise bound in the flat space limit. So when I take the flat space limit, only thing that I can say is that lambda 2 is larger than some minus c, where c is small and positive. That's it. So I cannot give you a precise definition of this constant c. Probably what it means is basically lambda 2 can be negative even in flat space, but the lower bound is actually theory dependent. So that's why there is not a precise bound that one can get from the CFT argument. And this is actually consistent with results of the recent results from Karen-Huot, Mazak, Rastelli, and Simmons-Duffin for d greater than 4.
What do you mean by theory dependence? So here, your theory is a scalar with self-interactions plus gravity. I mean, what?
By theory dependent, I mean like probably it depends on like what UV complete theory it comes from. So, for example, like without dynamical gravity, as I said, there is a bound like this which does not care about like what kind of UV theory you started with. But since I don't have a precise definition of C, that to me that probably the interpretation should be that there is no theory independent value for the say.
I see. But so going back to your pure scalar case, there in the massless limit, you also had a similar delta dependence, right?
Yes, exactly. That's right.
So there you would also say, so in a sense, you're kind of you're never quite reproducing the Adams et al. Result, right? Because you would say that there isn't a universal bound, at least with this method.
Without gravity or with gravity?
Let's say without gravity and in the massless limit.
Without gravity, even there is a precise bound, but like it's different from like. Let me go back to the bound. So as you can see, like these are for massless case, but all these bounds they have actually flat space limit.
Okay. So the positivity bound doesn't change even if there's this factor of nk, I guess.
Yeah, exactly. Yeah. All these bounds, yeah, exactly.
Because it's just the monotonicity that will depend a bit and the log.
Not really in the sense that if you look at this n of k factor, it looks complicated, but actually this is always order 1. It does not matter how.
I see. Okay.
So even if delta is small, it's order 1. Even if it's large, it's order 1.
Okay.
Yeah. So okay. as I said, so that means basically this lambda2 can be a little bit negative. That's allowed now. But this leads to a very interesting question. As I said in the beginning, without dynamical gravity, positivity of this lambda2 is actually related to the fact that in 4D RG flows, there is the A theorem. So because this lambda2 is related to delta A in 4D RG flows. So, but as I said, when there is dynamical gravity, lambda2 can be a little bit negative. So does this mean that the 4D A theorem is not valid in the presence of dynamical gravity? This is a really, to me, this is a very interesting question which should be explored further. I don't have much. How much time do I have?
You can take 5 or 10 more minutes.
Okay.
You started kind of late.
Okay.
Sorry, what do you mean by this question actually? So A theorem, I usually take that to, it's a theorem about CFTs, flows between CFTs. So what does that mean in the presence of dynamical gravity?
So what it means is basically the way you derive the A theorem is basically you study the RG flow in a non-trivial background first, and then you take the limit of the flat space. You take the flat space limit.
Mm-hmm.
So there basically, when you take the flat space limit, you don't make gravity dynamical. You just take gravity to be the background, and you just do the RG flow in that background. Mm-hmm. So what if I also, like, I take the flat space limit, but I also keep gravitons? So in that case, again, I'll end up with a very similar, almost the same identical effective field theory, but only thing that's different is that I also have gravitons. So then this argument will say that lambda2 doesn't have to be positive anymore. So that's why it's kind of confusing, because I would still expect that the A theorem should be valid.
Right.
So this is a really interesting question. I don't have a good answer to this problem, but like this is something that should be explored. There is another generalization that let me talk for a minute. So the same framework can actually be used to constrain effective field theories of multiple scalars. This is not just a trivial generalization. The reason I'm discussing this is basically there is conceptually this single scalar effective field theory and multiple scalar effective field theory, they are kind of different because there are new set of bounds that one can derive for when you have multiple scalars. So for example, obviously we'll have the same old bounds for this lambda coupling constants, because the bounds that I discussed before, they don't actually depend on whether you have other fields or not. So they are still valid, but now I have these other interactions involving both scalar fields. For them, actually, I have new bounds for this other coupling constant. The interesting thing is now they are bounds for odd k interactions as well. And another new thing is basically there are other more complicated bounds that comes from interference effects. So these two set of bounds, they are completely new. And the reason I'm spending any time on them is basically I think one of the motivation of this work is to actually constrain the 4-point graviton scattering amplitude in the future. And there, I think this new set of bounds will play an important role. And another reason I'm discussing this at all is basically this has a very nice application for RG flows with global symmetry breaking. Let me not actually, let me say a few things about this. So there are, especially for supersymmetric RG flows, whenever you break conformal invariance in the UV, sometimes that also breaks some other global symmetry in the UV. So let me just assume that in the you break conformal invariance either spontaneously or explicitly, and as a result, there is some other broken even symmetry in the UV as well. So in that case, you flow to the IR, which is described by some CFT IR, and you end up with a bunch of Number-Goldstone bosons. And this kind of RG flows are equivalently described in terms of dynamics of these number-Goldstone bosons. So this phi is the Goldstone mode associated with conformal symmetry breaking, and this is the axion associated with even symmetry breaking. And the effective field theory of this number-Goldstone bosons is completely fixed from symmetry. So there are only 3 coupling constants, and the form of the effective action is completely fixed. Now I can ask the same question: when this effective field theory can be UV completed? So that will basically provide some bounds on what kind of effective field theories you can get from this kind of RG flows. And by doing the same tricks, there is an exclusion plot. First of all, we still have delta A to be positive, since gravity is non-dynamical in this case. And there is an exclusion plot for other 2 coupling constants. So everything outside the blue region is ruled out. And so in RG flows with UN symmetry breaking in the UV, the effective field theory must lie inside this blue region. And there are many examples that you can check. For example, this happens naturally for n equals to 1 supersymmetric RG flows, which the effective field theory is actually computed by Bovev, Elbang, and Olson in 2013. That's basically corresponds to this black point, which is well inside, well within this allowed region. And this case, actually, the broken U1 symmetry is the R symmetry. Since the R current and the stress tensor, they're in the same supermultiplet. So when you break conformal invariance, R symmetry is also broken. Another example is basically a very simple example where you have a complex scalar field, which is massless in the UV, and you break conformal invariance and U1 symmetry by giving 2 different mass terms for the real and the imaginary part. So this flows to nothing in the IR. So in the IR, you have a trivial theory, and you can actually compute the effective action associated with this RG flow, and you can show that. In the limit, M1 goes to M2, but they're still different. It sits on the boundary, and as you increase the difference, this goes in. So this is also consistent with the general bound. Let me now conclude. So the main point that I want to again emphasize is that all effective field theories cannot be embedded in a UV complete theory. So that's the most important point that I want to say again and again. And more practically, effective field theories in ADS with or without dynamical gravity can be constrained directly from CFT axioms. So that means basically you don't have to assume anything beyond the standard conformal bootstrap axioms, and you can derive set of bounds. And more precisely, I showed that conformal bootstrap produces precise constraints on higher derivative couplings such as this. And actually, this framework is a very general framework, and there are many other applications of the same setup. Since the CFT theorem that I mentioned in the beginning, it is applicable even when you include loops or you have external states with spin. So a straightforward generalization of the work here can be done by taking loops or adding spin to the external fields. But to me, the most important application should be to use the same kind of setup to constrain graviton 4-point scattering amplitude. One thing I should actually mention, probably I forgot to mention in the beginning, I don't believe that the bounds that I showed you today, they are optimal. I don't think they are far from being optimal. And I also believe that there are similar constraints on odd K interactions as well. So I think stronger bounds can be obtained either from numerical bootstrap or from some more sophisticated setup. So one can explore that also. And on a more general ground, one goal should be to actually derive some set of asymmetric conditions directly from CFT. That will be really nice. And then one can actually use those S matrix conditions directly in the flat space scattering amplitude to derive bounds there. We don't have to go to ADS and go to the dual CFT picture to actually derive bounds. So I think there are many other applications of the same framework. So I truly believe this is just the tip of the iceberg, and we'll learn a lot more in the near future. So stay tuned, and thank you very much.
Thank you very much, Sandipan. Is there any quick questions before we take a break? Okay, if not, let me stop the recording.